Adsorptive removal of cadmium, copper, nickel, and manganese from environmental samples using iron Fe3O4 nanoparticles modified with zirconium oxide. Heavy metals are a significant environmental threat and a public concern worldwide. Metals such as cadmium, copper, zinc, chromium, and lead are among the priority metals that are of public health significance due to their high degree of toxicity. They can cause environmental and atmospheric pollution that may be harmful to humans. These metals are often derived from industrial waste from coal, paper, textile, metal plating, mining operations, and battery storage industries. However, they are necessary for living organisms but harmful when consumed in excess of maximum authorized levels. Hence, their concentration in the environment must be monitored and regulated. Sampling and storage was the first procedure of the methodology, where samples of an acid mine drainage were collected in a certain gold mine in Johannesburg, as well as a wastewater treatment facility in Pretoria. River samples were taken from APS River, and all the samples were collected in a 500 milliliters clean plastic vial and kept in the fridge at 4 degrees Celsius until they were used. The manufacturing of iron oxide nanoparticles was the second step. This was made according to the procedure described by Mononde et al. At 85 degrees Celsius, a ratio of 2:1 mixture of the salts iron chloride hexahydrate and iron chloride tetrahydrate was dissolved in deionized water under argon with vigorous stirring. The solution was treated with 25% volume per volume ammonia solution. The color changed from orange to black. The black magnetite was separated using external magnet and rinsed with deionized water to a pH of 10. Lastly, it was dried in an oven at 60 degrees Celsius for 10 hours before being crushed into fine powder with a pestle and mortar. For the fabrication of iron oxide nanoparticles modified with zirconium oxide, a gram of zirconium oxalate was dissolved in 20 milliliters of a ratio 5:3 volume per volume ethanol to water combination and maintained at 80 degrees Celsius for 2 hours with continuous stirring. From there on, 5 grams of iron oxide nanoparticles were added to the zirconium salt and ultrasonicated for 1 hour. The material was dried for 12 hours before being oxidized in a muffle furnace for 2 hours at 300 degrees Celsius. The result for the production of iron oxide nanoparticles modified with zirconium oxide were running in IR spectrum. A peak was observed at frequency of 3492 wave number due to the presence of hydroxide of the absorbed H2O present on the surface of the nanocomposite. The frequency at 1642 wave number corresponded to the NH2 present. Another peak was observed at frequency 400 to 800 wave number caused by the vibrations due to the presence of iron oxide and zirconium oxide. The band at frequency 1036 wave number and 776 corresponded to siloxane and silicon. A stretching at frequency of 2959 wave number and 1470 wave number was due to the CO bond and the methylene CH2. There was also a peak for the bonding of NH at frequency of 3456 wave number. Adsorption isotherms describing the interactions of the adsorbent with the sample with analytes in interest were assessed, and the findings showed that the adsorption capacity increased as the concentration of the analytes increased. Other adsorbents were employed to compare the adsorption capacity to that of iron oxide nanoparticles modified with zirconium oxide, and the studies showed a great maximum adsorption capacity for it. The pH of the sample indicates that the current adsorbent can be employed effectively in the wastewater treatment under certain operating conditions. The iron oxide nanoparticles modified with zirconium oxide was used as an adsorbent in the sample of water collected from the river, wastewater, acid mine drainage from several areas in Gauteng. Certain elements were eliminated entirely because they were only in small amounts. High concentration of manganese were discovered in the acid mine drainage, and wastewater samples, but the absorbent worked effectively with the removal of more than 90%. The current absorbent can be employed to extract the trace metals from the complex matrix such as wastewater and acid mine drainage. In conclusion, the capability of iron oxide nanoparticles modified with zirconium oxide to simultaneously remove cadmium, copper, manganese, and nickel in aqueous solution wastewater has been successfully evaluated, and therefore the synthesized adsorbent was found to be reusable up to 6 times and was effective in the removal of the trace metal ions from water samples. The following are the references for our research. We acknowledge the University of Johannesburg, South Africa, for the nanomaterial science research. We also acknowledge the financial support from the National Foundation of South Africa. Lastly, acknowledge the following analytical chemistry student: K. Mabilu, S. Kwabane, T. M. Mapola, F. Kosa, and A. Mabona for working on the research.